Hey, it's Mr. Krenz, and I'm going to go through problem 18 on the Chapter 7 review. So I'll assume that you have read the problem, you're familiar with what it's asking. A, how far will the cyclist coast before coming to a complete stop? So we need to answer a question about distance, even though we're only given the velocity function. So the velocity function is here, it's specified in more detail. Two main techniques or approaches you can go with. You could find the antiderivative of the velocity, which would give us the position. You'd have to find the constant integration, the plus c. The other way you could think about imagining the graph of this thing, and if you find the area under that, that would represent the distance that it has traveled. So I'm going to go with that approach. First thing, specify v in a little more detail than we currently have it. So I have v, which is equal to v naught. V naught is the original speed. That's at 15 meters per second, so it's going to be 15 times e, the base of the natural logarithm, to the negative k divided by m. K is given here as 4.2. M is the total mass. The total mass is going to be the cyclist's weight plus the weight of the bicycle. 70 plus 5, which is 75. So I'm going to do, let's see, what would that be? 4.2 divided by 75 gives me a 0.056, and then multiply that by time. So there's a more specifically defined velocity function. Now to start talking about the position, I'm going to see S of t. That's going to be the signed area under the curve, which I can represent as the integral from 0 to time t of the velocity function. 15e to the negative 0.056. Now here I'm using t as one of the bounds of integration, so I'll have to change the variable integration. Let's choose x here. Yeah. So this represents the distance traveled from 0 to time t. Right. I'm going to actually integrate here and make this a little more specifically defined. I can factor that 15 out, or just pull the 15 out. And then if I integrate here, integrate the exponential, that would be e to the negative 0.056x divided by negative 0.056x. Oh, not x, thanks, 0.56. Right? Essentially like doing the chain rule backwards. Then I need to evaluate this from time equals 0 to time equals t. Okay. Now actually plugging t in for x and 0 in for x, I would get 15. Actually here I'm going to simplify things a little bit. I can do 15 divided by negative 0.056. Gives me negative 260.857. E to the negative 0.056x. Right. And now actually plugging in t and 0. If I plug in t, it becomes the same expression but with a t. And I'll subtract this expression evaluated with x being 0. If x is 0, that's going to make give me e to the 0th. E to the 0th is 1. So I'll just have a negative 267.857. If I'm subtracting a negative, it will turn into addition. So here is my position function. Right? It's not the answer to the question they ask, but it's going to make that easier to find. So I can plug in any time t, and this will tell me how far it's traveled, the displacement. Now to find how far it's traveled, so how far will the cyclist coast before coming to a complete stop, what we can do is take the limit of s of t as t goes to infinity. So as it coasts and eventually the velocity hits 0, how far does it travel? Well, if I look at the position function, if I set t and then make it huge, I'm going to get e to the negative huge number, which means that this term is going to become approximately 0, which means this whole term here is approximately 0. And the answer would just be the constant we're adding, 267.857. 0.57 unit. We're dealing with meters here. So by the time that the cyclist comes to a stop from their coasting, they'll have traveled about 267.857 meters. Okay. Part B, how long is it going to take for the cyclist speed to drop to 2 meters per second? Well, that'll mean just taking the velocity function right here and setting it equal to 2. Make sure I copy that right. So this is just solving the exponential here. So first step here would be probably dividing by 15. 2/15 is equal to e to the negative 0.056t. Natural log both sides. Essentially cancels out the exponential, so I get negative 0.056t. Divide both sides by negative 0.056t, and then drop it in your calculator. And you should get, let's see, negative log of 2/15 divided by negative 0.056, approximately 35.980. We're dealing with seconds here, so that's in seconds. So it'll take almost 36 seconds for the velocity to drop down to 2 meters per second.